Thank you very much, all for coming. Yes, early 8 a.m. in the morning after a party. I'm very grateful for you all here. So I must work even harder this morning. The very first example of modeling and simulation, which is how I have lived for 30 years, the one I like most is the Living Heart project. Maybe the Blue Brain project, when we announced it, will match this, right? Basically, the team funded by the National Institute of Health is trying to build as faithful a representation of the human heart as possible with three multi-physics models in it. Number one, of course, the physical, pumping, right? Number two, the fluid dynamics, blood flow. And number three, electrical, because that's how the heart works. Combining the three to try and represent the heart. Yeah. One of the early application of this model is the insertion of the pacemaker. I didn't know until this that pacemaker isn't a device you attach to the heart, but actually a wire you insert into the heart. Yeah. Why is this important? There was a 2-year-old girl who had the wire inserted, and by the time she was 20 years old, the wire broke 3 times, and she had to be operated on 3 further times. Yeah? And the reason is it's not hard to understand for those in mechanical engineering, which was my first degree. When the heart pumps, one of the researchers actually put a hand underneath, in this case, an animal heart. And when it pumps, it feels actually like a rock. Yeah? And you can see in this particular case, this particular corner, if you ask a mechanical engineer where the brake will be, it will likely be here. Yeah. And we don't realize that in 20 years our heart pumps about 1 billion times. Yeah. And therefore, likely failure. So they're using this for accelerated testing of insertion of wire now. They're also using this to test arrhythmia for new drugs that are coming online. These models are built top-down, and this is how I've lived for 30 years. Essentially, we get our scientists based on laws of physics to build a model, and if there are no laws that we can rely on, that people can agree to, we get an expert in, and then we codify the expert knowledge into a set of rules, if statements. And we build our model, after which we send in the initial condition, and hopefully we get a good prediction. Yeah. I like to use one more example before I move to the blank area on the right here. This approach of top-down. This one I like because in working with NASA, I also realized something. This is supposed to be Earth, and that's Mars. And when you travel to Mars, you don't plot and aim for Mars, right? You aim for where Mars will be. And you can see it's a path you plot, right, to where Mars will eventually be. And I asked NASA, what laws do you use? This video is from ESA, the European Space Agency, but I asked NASA, what laws do you use to get this right? I didn't realize that they still rely on Newton's equation, 300 years old, and it still works. Yeah. And they tell me it works for all planets in our solar system. Maybe with the exception slightly of Mars, yeah, they say. Because Mars, you get it slightly off, but still okay. Then I asked why. Well, apparently, not Mars, sorry, Mercury is slightly off. Yeah? Exception of Mercury, slightly off. Then I asked why. Because Mercury is too close to the sun, and apparently the gravity of sun warps space-time. Yeah? And apparently then, at that time, you better switch to Einstein's equation to be more accurate. Yeah? So that's why Einstein is also famous. Yeah. So that's a law we use, right? So all planets in our solar system except Mercury. Yeah? It works. So again, we build, we put it there, right? To try and make a prediction to where things will be so that when we arrive there, it will be there. How about the financial markets? Do they use laws? Yeah, this is an interesting one, right? Yeah, you would have thought they only use rules, right? Until I arrived in Wall Street, spending more time there. And apparently, all cash in the world is $10 trillion. all stocks in the world, $100 trillion. All bonds and debt in the world, $200 trillion. But all that is nothing compared to this big $500 trillion of derivatives. And in fact, this is the problem of the 2008, right? For those who know. What is a derivative? A derivative essentially is a bet on everything else. Yeah. How do you price a bet? Right? This is the bet where you call, buy, and put the bet, and it varies, right? In real time with all these things. And do they use an equation to model this? Yes, they use a partial differential equation, like fluid dynamics, to model this bet. Because this kind of bet is like as though you go to a race course, and then you buy the bet on this horse for $10, and it is a 10-to-1 odds. Never mind, you buy it, right? The race starts, and somehow your horse is in front. You're very happy until someone taps you on the shoulder and say, "Can I buy your bet? How much you want me to pay for it?" How do you price that bet? But your horse is still running, right? It's ahead. But as you are deciding how much to sell your ticket for, your horse lead is changing in real time, right? And that's exactly why you need a partial differential equation, right, to model pricing of bets. This won the Nobel Prize in economical science, right? Scholz and Merton won it. Black passed away. I like to think that Merton, who came later, got the prize, right? Told everybody to only call it Black Scholz. It's very nice of him. Yeah. Right? I thought someone was clapping. Right, anyway. So that's the law, right? You apply this equation in there, and you do a prediction of, okay, this bet today, if sold, should be priced this way. Yeah. Do they use rules? In fact, they do it all the time, even more often. Basically, whether you buy or sell the stock, if the short-term 50-day moving average of the stock cuts over the long-term 200-day moving average, right? Once it cuts over, don't talk to a human. Machine just go ahead and buy. That's basically what they do in algorithmic trading. I've simplified it a lot, but actually that's what they do. Right, of course, they add their own secret sauce to say, don't buy if it is a Friday and it's raining, or something along those lines, right? There are secret sauces around, but fundamentally, the concept is this, yeah? That's it. This is how the world has mostly lived in the prediction era, all these years. Then, a few years ago, the leaders in alternative thinking, because they make a lot of money if they did in the financial market, starting to do something different. They said, there is a new way that needs to be augmented. This new way is, don't tell me anything about laws. Don't tell me anything about expert knowledge, right? Just give me your history. And just looking at your history, I will try to make a prediction. Why, I asked them, did they start thinking this way? What motivated them to think this way, right? The answer was, they said, the Black-Scholes equation in the stock market, based on laws, could not predict irrational behavior of humans. That was what I was told. Yeah. Now, economists traditionally have, for decades, assumed that humans are rational. Yes, you can look that up, right? If you look at economics throughout the decades, most of it assumes that humans are rational, and then they build theories based on that fundamental starting point. Last year's Nobel Prize for economical science, was awarded to behavioral economics, trying to take into account the fact that humans' rationality change, right? They can't handle it on the left. However, they told me, embedded in history are irrational behavior of humans. That was the motivation for them to use a second model approach that relies on history. So that really got me to realize why they were motivated to do this earlier than everybody else. Yeah. So how do you build a model like this when you have nothing to rely on. Well, what you do when you write your computer program is just give your computer program a set of adjustable, self-adjustable dials, one for each parameter that affects your prediction. And every time a new history element is brought in, the dials are adjusted a little bit, the next one adjusted a little bit, and after 1,000, 10,000, 100,000, and Google's case, 1,000,000 examples, the dials get all adjusted to a pretty good place to make a prediction. Fundamentally, that's what machine learning is. I've simplified too much. For those experts in this field will probably scold me, but let's start with this. Yeah? Fundamentally, that's what machine learning is. You write a computer program to self-learn, and the way to self-learn is to give it adjustable dials, and the way to get the dials adjusted to the right places is to give it lots of examples. Just remember this, and you are good, well-grounded, yeah, for machine learning. Don't let anybody scare you. All right? Start there. All right? We'll talk more. Let's have a look. So a few years ago, I had to go back and try this, right? The Wall Street people tell me this. I think I better go back and try it myself. So I asked one of my engineers that had 2 weeks free. So I asked her to go and take an online course for machine learning. This is a Stanford University course, online course by Andrew Ng. After she came back, I said, predict for me whether it will rain tomorrow at San Francisco airport. Oh, no physics, huh? Don't talk to any meteorologists. All you have is the 4 decades of weather reports of San Francisco airport. That's all you have. Okay, don't talk to me and come back when you have the answer. Now, this is the guidance I gave her. So what she did after the course, she gave each of these things in the weather report adjustable dials. Right? Technically speaking, she gave it all 10% to start with. Each of them had 10% contribution to the prediction, whether it will rain tomorrow. So 4 decades is 15,000 days. She sent in the first day, checked the answer for the next day, sent in the first day, and the machine guessed rain, and checked the answer next, no rain. Okay, wrong, adjust the dials. Second day, third day, 1,000 days, 10,000 days, 15,000 days. She got this. Meteorologists are predicting rain, no rain at San Francisco airport, 90% accurate. Just this ratios alone is predicting accuracy 82%. Now, not as accurate as science, but now it's pretty fast. It's just a mobile app, right? You plug in today's weather, and you do the ratios, and you get tomorrow's rain, no rain. This is a almost synthetic example, right? A simple example, but it made me realize how things work. From going to an online course all the way to doing a prediction, gathering the data, doing the prediction. 80% of the time, she was spending cleaning up the data, formatting it right, because 4 decades, the data come in different formats, right? Yeah. So you will also realize that through this exercise that, data preparation is going to be key in training your machine. So now, it is quite usual in many of the advanced industry of prediction, yeah, where they, for example, make a lot of money if they predict better than just the neighbor, right? They are now augmenting it with the thing on the right, the bottom-up approach. The gold standard still has to be this, right? Because this is true and tested. This one, based on history, may be less accurate, but it's very fast. The other problem with this is that it may be sometimes opaque. It gives you a prediction, and sometimes it's very difficult to validate why. Yeah? But at least on this one, you can. So the two has to work together. So I summarize all these different terms. Don't worry about these terms in machine learning. If you're uncomfortable, just close your ears for the next 3 minutes. Right? Basically, there are 2 ways, top down, bottom up, and then today we are just focusing on bottom up, right? There are two things you do in this approach. You either predict a point, which is, tell me the stock price tomorrow, or you predict a category. Should I buy or sell this stock tomorrow? It's a very different question you ask, yeah? For predicting a point, People in statistics will know this is regression. Give me all the points, I put it on a piece of paper, scattered all around, and I just try my best to draw a single straight line that somehow satisfies everybody, although it's very tough. Yeah? Right? So that's regression. And once I've drawn the line based on all the points, I just extend the line out slightly, and that becomes my prediction. Yeah? Regression. Predicting category is where we will talk more about today. There are 3 things you could do. There are more. I'll just talk about 3. One is classification, and that is when you have data and your data is labeled. Or by label, I mean I have a picture with lots of things in it, but I say there is a cat in it. Right? Or by picture of a farm, I can say there is cabbage in it. Right? It's called supervised learning when your data is labeled. When it is unlabeled, tougher. It is just a bunch of images, no labels on them, and you throw it to the machine and say, just somehow figure it out. Google tried this, right? Andrew Ng and Google tried this with tens of millions of images. Just put it in, and all the machine can do, because there are no label, can't classify them, all it can do is cluster. After going through a data center full of computers, running through weeks, going through tens of millions of images, the machine came out with 2 big clusters. The machine didn't know what they were, but humans went in to have a look. The biggest clusters were cats. Second biggest cluster, humans. Yeah, right. Apparently on YouTube, you got more cat images in it than humans. Right? Yeah, there we go. So when you cluster, the machine can't tell you what it is, but at least it can group things together, and then you come in and inspect. And then finally, there is reinforcement learning that doesn't use history. It just takes 2 machines, like in a game, especially you have the rules of the game, and just let it play with each other billions of times until you somehow learn it. Yeah? Just randomly play. Not in a smart way, never mind. Yeah? But after 1 billion, you get smart. Yeah? That's reinforcement learning. And then lastly, this last column, don't worry too much, are all the different terms. You will hear them, right? Deep learning, random forest, support vector. Don't worry. These are just names people give, right? Like, in automobile, right? I have a blue car driven by a person with long hair wearing sunglasses. Give it one name. Support vector machine, right? Someone driving a truck, right? With a crew cart, right? Sipping a Coke. Give it another name. Call it random forest, right? Just treat it like that. Right? Don't worry too much about it. And these are all the relationships. Yeah. That's machine learning. A machine learns to be artificially intelligent. All right. I give this introduction because the next set of slides, next part of the presentation, will rely on this. Yeah. Deep learning is the hottest because somehow it is great at classification, and people have found through a technique called backpropagation to adjust those dials, right, to the extent that it's really great at classification, as well as things like that have a time series, yeah, for those who have who understand recurrent neural networks, and things that have spacing as they are going through time, LSTM, long short-term memory. These are all the different names you get. People give it a separate name, right, when it does something different. And I highlight that is because billions of dollars have been spent, yeah, by the Googles, Microsoft, the world, particularly on that. But I must emphasize, the whole world isn't just deep learning to become artificially intelligent. There are so many other ways, right? Yeah, I won't cover why, but for those interested, maybe we take this as part 2 of the lecture. Okay. There are 3 things that has the most money invested in the industry related to this chart. 3 areas. I want to emphasize them is because if you want to do something in machine learning towards artificial intelligence, don't reinvent the wheel. If you can rely on one of these 3 things, use it. Because billions of dollars have already been invested in it, right? And I explain why. The first one is image classification. Understandably, Google with YouTube will be very keen to classify images well. So the world got together, ImageNet, the community got together, pulled together 14 million images and say, everybody come, classify these images and compete, see who is better. Yeah? 2010, 2011, the error rate of those computer vision programs, hard-coded programs, not machine learning, right? Hard-coded programs for image recognition were making 25% errors of these 14 million images, while human, like B for brain, made only 5% error. Some poor person, right, they had to go through that, right? No, I'm sure they took some sample, I don't know. Yeah, they somehow measured the error rate was 5. Why? The machine didn't do well then because they were hard-coded. They could recognize paintbrushes very well here, but not there. They got confused. Humans were better, right? Humans could somehow say, yeah, I think this is a paintbrush. Yeah, this is related to paintbrush. But the machine couldn't at that time. The machine with hard-coded programs could recognize sunflowers very well here, but not there. They failed there, right? Maybe here is because if you hard-code your program, you will think this is more sky than sunflower, so let's call it sky, or something along those lines, right? Because you have to anticipate all these different nuances, if you hard-code things. So the world got together and said, we're going to change. We're going to use the deep learning method, build a set of neural networks, and give the connections on these neural networks all these adjustable dials. They call them weights, right? And just send in examples and keep adjusting your dials in your different layers, right, until you recognize well. Then you use it for prediction. 14 million is pretty good set, to keep trying. And by 2017, the error rate has dropped to 2%. It is done. Image classification is essentially done. If you want to use it to assist humans, you can rely on it, provided you have enough of a big enough labeled training set. First message. Second message is 2% is not 0%. So if you use this, for example, for autonomous vehicle, don't expect it to be perfect. Keep that in mind. I don't know of any image classification that has 0% error yet. Because it's essentially just based on history. Right? It can still make mistakes. So better still apply rules on top of it. One early application, I like this one the best for now. These farm combines, when they build these farm combines that go and spray herbicide on the crop field, currently they blanket spray the entire crop field. Herbicide. They just spray the entire, some even fly a plane, right, to spray them. 2 Stanford University students, after attending Andrew Ng's course, has a relationship with a farm and say, why don't we just go out and take pictures of crop fields? So they went in and say, cabbage, label, wheat, label, cabbage, label. After 10,000 images, they trained their machine to differentiate between cabbage and wheat. Right? And then they did a startup, got some money, grew it to 100,000, and then John Deere applied them. And here is the result. So instead of blanket spraying the crop field, you now only differentiate between crop and wheat and squirt. You notice the blue streak? So as it goes over, crop, avoid, wheat, squirt, right? 90% reduction in herbicide use. Good for the food we eat, good for the farmers in cost, good for our land. So this company liked it. You know how much they paid for the data? $300 million. These 2 kids are really happy. Another lesson here, right? In the past, companies buy companies because of their secret methods. Now, companies buy other companies because of their well-classified data. See, the world has changed. I'm not saying the methods are no more important, but I'm saying data is becoming also highly valued. You see, drug companies buy other drug companies. A lot of it is because of their data. Another area. These are log files that comes from network and data center. Let alone the fact that IoT will make this even bigger. When we are in cyber defense, we spend a lot of time analyzing these log files in a text-based way. We thought, Billions of dollars has been invested in image classification. Can you convert a log file to images and use image classification? We did. In the product called Introspect, we converted each day of a log file for every user, every server, every IoT device. Give it one set of images to say this was the behavior of this user for this day. That's 24 hours in a day, and that's minutes in that day, in those hours. And then train the machine to say, this is normal, this is normal, this is normal, this is normal. And then when something abnormal has come along, alert me. So this is one example where we realize that billions of dollars have been spent in image classification. Don't reinvent the wheel. Can we convert a problem to leverage that? Next area, voice and speech transcription. To transcribe speech to text, the training set was 100 million words. Next challenge. To translate one language to another, WMT got together with EU funding to try and translate these 7 languages well, with Chinese to English being one of the bigger proposals because of the big market here. This one needed 1 billion word training set, huge. Another lesson. The first thing I wonder, where are you going to find 1 billion words of English and Chinese, right? They went to the United Nations. You see, you can be creative about where you get your data from. United Nations, years of professionally translated text, right? They train the machine. In this case, Microsoft has just announced, as of March of this year, Chinese to English translation matches professional human quality now. So that's done too. I'm a bit bold here today. Yeah, no HPE marketing people here who will recommend that I don't do a live demo, right? I downloaded this app. There's a whole list here. I mean, A to Z, and even includes Klingon, right? ABC. I picked Danish. Anyone who can understand Danish here? Okay, all right. I'm just going to speak into it, right? I took a cab to the airport and got an earlier flight.
Jeg tog en taxa til lufthavnen og fik en tidligere flyvning.
Yeah. 3 things, right? 1. 3 things, right? Yeah, there we go. 1, my English speech, I don't even know what accent I have, right? I lived in 5 countries, and the machine understood it. I didn't have to train it, right? My accent. It converted to English text, did the translation to Danish, and spoke in Danish, and with a delay of 1 second. Yeah? And it was done well, and the pronunciation was educated, huh? Yeah. Right? So I was really impressed. The first thing, the people who read papers and try to monetize their data asset were the call center people. You imagine how much valuable asset there is sitting there doing not much. From all over the world, imagine big companies, right? They are transcribing into text those recorded voice, translating them to one language that they will run analysis on. Of course, they cannot, this has to be private, right? They of course cannot share and sell it, but they can use it internally because they got permission from you when you called in, right, to the call center. This conversation will be recorded, yeah, right, for training purposes, right? Yeah. But in the moment, training purposes requires you to listen through the recording again. But now, once you converted it to text, you can analyze it with tools. Yeah? You see how the world is changing now, right, given all these assets. We do have a customer that is already leveraging it. Basketball fans? Actually, I should be asking for soccer fans now, right? But basketball fans, have a look, yeah? Every game, court side, you will notice that 9 cameras are looking at the game, but courtside you can see someone actually speaking, who got the ball, who took the shots. These are like commentators in soccer also, right? So they are converting this voice recording into text and then embedding the text onto the video. So that now you can search the video based on the commentators. And then NBA now allows someone to go on their website and say, Magic Johnson that took a shot during the peak of his career over 3 years, execute. And then the robot just go in and just pick all these commentators' voice, right, that has been transcribed, search them, and then just pull out 30-second sections of them. Right? Create an MPEG file, and NBA sells it for $50. Otherwise, it's sitting in a warehouse. Or it costs a lot of money for someone manually to extract it. Turns out the biggest buyers of these clips were competitive teams trying to study the other players. Yeah. Okay, I've done imaging, highly invested in, understandably, because Google has YouTube. I've done speech, highly invested in, billions of dollars, because Microsoft has Skype. You see? I'm just guessing, right? There is a third area, which I'm going to show you next. This third area is related to the fact that the first two does not account for the fact that you have adversaries. You have opponents that are making strategic decisions against you, and you have to adapt your strategy. As such, nothing epitomizes competition more as much as Formula One racing. Yeah? So this is the Williams team. How long does it take for us when we go to a shop to change the 4 tires on our car? Yeah. Yeah? Look at this one. Yeah. Out, in. 1.92 seconds. Another view. Out, in. One more time, yeah? It's a very satisfied person here. Nodding his head. Yeah. Even with 2 seconds of pit stop, it's still too expensive to do a pit stop. Yeah, because the minute you stop, people overtake you, right? However, if you don't do a pit stop, your tire wears out and then you run slower, or worse, it blows and then you become last. That's a very, very tough one. And under certain tracks, you say, I rather do a pit stop because it is easy to overtake this track. But there's another one that says, this track is very difficult to overtake. I don't do a pit stop and I risk it. In the Spanish GP, Mercedes, Lewis Hamilton was number 1, and Red Bull was number 2. That has already done 2 pit stops while Hamilton only did 1. The dilemma was, does Hamilton do his second? Which others have done. They decided not to because this track is difficult to, this track has certain characteristics. So the strategists say, don't do a pit stop. Just drive carefully. Imagine telling a Formula 1 driver, he won. Yeah, he won. Yeah. So the world got together again for a benchmark and said, okay, we use games. Yeah, we know IBM beat Kasparov in 97. 1047 is a number combination in chess. These are big numbers, yeah? 1047 is so big that if I got all the computers available on Earth, put them together, run the calculation for chess for 100 years, I only do 10 to the power of 38. Yeah, so this is crazy numbers, yeah? So you don't solve chess, you only beat humans in chess. Yeah? A few people realized in 95, University of Alberta built the checker program that beat the world top checker player. 1020 just been solved. Yeah. It took them 15 years on 200 servers at University of Alberta to ultimately solve it, even though in 1995 they beat the humans, but they haven't solved fully chess yet, checkers yet. Recently they did. You know what the conclusion was? If 2 machines are playing and don't make any mistakes, the result will be a draw. You see the whole paper, right? You go through the paper. Yeah. At the end, conclusion, draw, right? Yeah. If you were a computer science student, this will be your homework. Yeah. 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 The reason is 1,000 combination, your lecturer can check your answer exhaustively. Yeah, wouldn't take him or her the whole night, right, on one paper. Yeah. Now we know Google beat the world top Go player. That's a super crazy big number, right? I don't know if it will ever figure this one out exhaustively, but the machine got good enough, both in machine learning way, classification, supervised learning way, and also later AlphaGo Zero, the reinforcement learning way. Yeah. There were 5 games Lee Sedol played against AlphaGo. Lee Sedol only won 1 game. And this is the last move of Lee Sedol that he won. You see that number 80 at the bottom? This was his last move. Take note of that. And this is where Lee Sedol is the only game Lee Sedol won. So if you find this on the internet, keep it, because this, for posterity, this is the last bastion of human triumph. Yeah, since then, the machine has not lost. Right. So you notice a blank area on the right here. It is us figuring out what to do next. Yeah. We decided for poker, right? Imagine, right? Established company saying that we're going to build a poker machine. Actually, no. The reason for poker, because it's imperfect information, different from everything else. Even though the number of combination in heads up, no limit, Texas Hold'em, this is the version of poker, is 10-160, still a crazy big number, not as big as Go. It has one thing that is more complicated, and it is because it's imperfect information. The machine does not know the opponent's cards, unlike the others. It is hidden from the machine. So the machine has to deal with a level of uncertainty because you don't know your opponent's cards, number one. Number two, and the opponent is constantly trying to deceive you in poker, right? So we believe this is more attuned to business negotiation, auctions in financial world. So we went with this with Carnegie Mellon University, Liberatus. Professor Sandholm is the principal investigator. And you can see we went to compete against one of the four top poker players in the world, 4 of the top poker players in the world. One of them is on the right. There are 4 different rooms. And you can see us very innocent on the left. You'll notice the cable at the bottom, running to a $10 million computer behind. Right. Didn't put it in front, yeah. 2015, we lost $700,000. Yeah, Professor Sandholm got the money from the NSF, National Science Foundation, to build this system. I felt for him when he had to report to the NSF he lost. Yeah, right. Yeah. True to form, NSF usually gives you a second chance, just like the gravitational wave experiment. It was a second chance that he got the Nobel Prize, right? They gave him a second chance. So we asked the 4 top poker players, what was it about the machine that you managed to outwit? They said, it did not bluff very well. Okay? So Sandholm went back and said, I want to retrain my machine, just focus on bluffing. All right? He said, it'll take me 3 years on the same machine, so we brought him a machine 10 times bigger, right? And went back in 2017, we won $1.7 million, yeah? Yeah. You see, these are few lessons, right? If you can identify the weakness, right, it can be fixed. Yeah? So we asked the 4 top poker players, so what's different now? Oh, they said, it bluffed really well now, yeah? It almost bluffed like as though it is cheating like an alien. Right? These are the kind of comments you hear. Well, the whole point about bluffing is that it is unexpected. Yeah. This is now on record, and so far, Liberatus has not been beaten since. Lots of people competed. He has not been beaten since. Yeah. So poker's done too. Yeah. In particular, heads up, no limit Texas Hold'em, right? That particular kind of poker. That's Professor Sandholm on the right. We are retargeting it for race strategy. We are retargeting it for business negotiation. Imagine the future when you negotiate with someone with an earphone, be a bit wary, right? Whether there is a machine supporting that person. And you see people auctioning on the phone, yeah, these days. You can see auctions, right, like Christie, and then on the side, people holding phones. You're not sure if the other end, there is a bot here helping the person, right? So these are the kinds of things that could be changing, right? We're not saying now, but it's coming. Okay, I'm almost done. I close my session with this. Data goes to analytics, and when analytics got too heavily loaded with the size of data, you build machine learning that can learn on their own with adjustable dials, and then they become artificially intelligent once they have learned enough. But once you give them the ability to act, they become autonomous. See, the key thing of an AI system becoming autonomy is the ability to act. And this is where I just want to show you this very quick video, right? Oh, never mind, I keep going. This Atlas from Boston Dynamics, yeah, sold by Google to SoftBank. Work to do, never mind. Let's do some work. Not very nice. No. Who felt a bit bad for the robot? Yeah, don't worry, it improved the next year. It is doing this 1 year later. And then, 1 year after that, it is doing this. Yeah. All right. On that note, thank you very much. Yeah.
Out of words. I'm baffled. Yes. What is there left? What game are we trying to ask the machines to bid for us? Is there anything left?
Yeah, there are many different ones. People are trying conversational bots, right, that can pass for humans. That one, some are saying they feel a bit uncomfortable. They just need to be told that it is a bot ahead of time. Some insist on that. I think this is the next area where you start not being able to differentiate in a conversation, whether the other party is human. Yeah, I think this is the next big area. We're almost getting there. Some of them are passing really well, right? But then, can you carry a conversation that is more advanced, that has more nuances? You start to spot it, right? Yeah, I think that would be the next, that's a big area. We can have a good accompaniment, right, that way. Imagine, so we are working with NASA for long duration space travel. Going to Mars is 9 months to a year, and then coming back another 9 months to a year, right? Let alone staying on Mars, right? So it's a very lonely period, and socially, we humans need to be social. We are thinking that each of them carry with them an increasingly learning conversationalist, for example, right? So these are the kinds of things, that has value, but it could be also, like many things, exploited. Yeah. I'd like to show you on that note, right? Sofia, my favorite. Volume, please. Yeah, on that note. Yeah.
Sofia, we want to thank you for this conversation.
Thank you, Andrew, and thank you everyone for inviting me here. By the way, if you're interested in giving me an investment check, please meet me after this session. Otherwise, have a wonderful rest of the event.
I like this part, yeah?
Okay.
You can see the smile is really good. Yeah. Now, you will see that they have intentionally showed you parts of Sofia that is robotic, because when it gets too close to human look alike, some humans say you pass the uncanny valley, which you feel a bit creepy. Right? We humans have that issue. So currently, they intentionally tell you this is a robot, right? Yeah. So we are reaching that point where these kinds of areas, there's more emotional, starts to come in. Yeah. Mm-hmm.
Do you have any? Yes, please pull the microphone towards you. And
question about the ethics title of your second to last slide there, which you didn't talk much about. I'm curious, what is HP? What discussions is HP having internally regarding ethics of AI, particularly as you move up this diagram?
Brilliant. Yeah. Actually, you helped me complete this slide. Yeah. Thank you. Actually, those two questions are related to continuation of this talk, which was running out of time. That's why I stopped. But thanks. Now I have a chance, right? Now, intelligent system given the ability to act becomes autonomous. Autonomous system given the ability to make a contract, pay for things, become independent. It's just like kids, right? You Once they go to school, they become intelligent, yeah? And then they have transport. They become autonomous, right? They can go out to malls. And then once you give them a credit card, they become independent, right? For example, right? Imagine an autonomous car like Uber going around that has bitcoins. Doesn't need us anymore. It's driverless. An autonomous driverless car doing the ride sharing, goes pick up people, and then get paid with its Bitcoin. And then when it needs a fix because something is broken, it does a reverse auction to the workshop, say who wants to repair me. It drives itself to the workshop and pays the workshop, right? So you can actually let this autonomous vehicle go for 5 years and say, return to me in 5 years and give me the money you have in your bank, yeah? Right? They become independent, yeah? Right? Imagine, I like to use the example where you wake up in the morning, you look at a toaster, you negotiate with the toaster to toast your bread, right? Right? And then one day a knock comes and the repairman says, I'm going to pick up your toaster because the toaster are called to be fixed. Yeah? And if you've not been treating it well, it doesn't come back. Yeah? So we are, to answer your question, we are looking at independent things. So to me, IoT is not Internet of Things, but independence of things. Yeah? That one is even more next level up of thinking. Yeah, we are working on this by giving an iRobot bitcoins, for example. It goes around cleaning rooms, depending on who's willing to pay more. Yeah. So we have a demo in the lab. And then finally here, we won't have time to cover them, right? To me, sentience is when the machine feels pain. Next level up, conscious, is when it is aware of others. And the most difficult one, I think, is self-awareness, where it's aware of itself. Yeah? We humans are not self-aware until 18 months. And very few animals are self-aware, right? So we won't have time to cover that, but these are questions we ask. Yeah? And a lot of them related to jobs. We have time? Yeah.
Yes, we have one more time. Time for one more question, and then.
Yeah, what you showed.
Yes, please go ahead.
What you show is really interesting in terms of computation power and memory. But if I compare the power used for this computation by a human brain and the kind of system that you've shown, it's clear that the human brain beat it. So with the limited available power on Earth, is it possible to generalize that to more than a couple examples of a couple of people?
This is a brilliant question, right? I use this example here, right? When you're doing clustering, right? For example, on a machine that is a data center size, you probably be using a few hundred kilowatts of power, close to a megawatt. The biggest one we built is about a megawatt to just run machine learning very quickly. Our brain, one slice of pizza of 300 calories, will run it for 3 hours. Right? So we are far, far away in terms of power consumption. Intelligence is essentially limited by power. Yeah? And the amount of data available to consume, good quality data to consume. But computational capability is increasing for the same power. You are seeing that. But it takes Moore's law at best, right, to give you that progress. So we will be limited in intelligence in a way by Moore's law until perhaps quantum annealing comes about, which we are working on, right, to give you the learned gradient descent learning much faster. Yeah, so we need a new technology. The current technology, intelligence will grow as fast as probably Moore's law. Yeah.
We had a question earlier here.
Yeah, hi, thanks a lot. I come from the field of climate, so I want to go back in history, talk about back in the day, meteorologists used to do what you now call machine learning, basically pattern recognition, draw contours on maps and predict what will happen. Then John von Neumann came and said, I've invented a new machine which can do this a little better. And in fact, the first meteorology paper, von Neumann is a co-author in 1950. And it took about 10 years, and then it turned out that solving PDEs, partial differential equations, is better than pattern recognition. Have we now turned the clock? We are going back to before von Neumann, and it's like, I don't know.
That's a great question.
Yeah.
In fact, it's a similar question the financial people ask. It's a similar question engineering people ask when they predict models. I think what we are turning back to, as you say, is to use both, not one or the other, right? One of the comment I heard, right, a few years back when I gave this talk, one of the climatologists in the US went back, tried this out, and came back and gave me this comment, right? Actually, my model worked throughout the year, and it is great, physics-based. Except for the month of June, there's always this anomaly. I couldn't figure out why. But over the decades, I've adapted my model to deal with the anomaly. And we do have that, right? Anomalies, right? And it's regular. Until he said, okay, now that I have so much history, right? I train my model, and somehow the model is predicting June well. This tells him that the answer is in history. He didn't know, the bottom-up way did not give him the answer. It only told him that the answer was in history. Then he went in and looked, he realized what it was. Yeah. So you can see now that the bottom-up way gave him a new perspective on things that resulted in a discovery. So the answer is use both.
I add the point. It turns out that science has been using both. You cited Newton's law. About 100 years before Newton, there were a few gentlemen who were observing the stars, and there was a mathematician who was modeling with that data and derived what we know as Kepler's law, that were the basis to derive the top-down theory. So
we've been using both
so
all
we
these
understand
years.
This is really has started around the time, in the 1600s.
I should use that.
And was fundamentally new compared to anything that had happened before.
I see. Very good.
Final comment.
But the computers are helpful.
It's something else, right? You needed the computers, right, to gobble up enough data so that your prediction can be, in this case, right, 82%. I was hoping the fact that if you can do 80% or 75%, you'd be great, yeah. But because of computers, it got good enough, yeah, to come close to physics. Yeah. Not there yet, yeah.
There is a phrase called climate change, unfortunately. Climate is history, and climate change means history does not work. So that's something to think about.
That's true too. All right. I'll remember that comment. I'm still learning, right? Yeah. Okay. Anything else?
If there are no more questions, I just want to invite everyone to stay in the room. The panel will begin in 5 minutes. Thank you very much. Let's thank
you.